And I gave you what I would think of as two somewhat surprising algorithms. The randomized one was less surprising, the deterministic one more surprising. But to show you that using divide and conquer, one can come up with fairly remarkable results. And today I'm going to give you two more examples. Both of these examples really had a huge impact on the world of mathematics. And they were basically just doing divide and conquer. So I'm going to start with, sorry, let me first switch that sound off. The first question, which is actually a very natural question, is an algorithm to multiply integers. Something that we've all learned from, I don't know, maybe when you were 6, 7, 8, maybe not 6, maybe about 8 or 9, right? When you learn how to multiply. And so let's actually revisit multiplying two integers. So we'll think of the input, because now we're computer scientists, so we think in binary, as two n-bit integers. Although the argument is going to be equally valid for whether you're doing bits or normal digits. What is the running time of long multiplication? What is the running time of long multiplication? Right, and log multiplication is the multiplication that we all know and love, have been doing since grade school. What is the running time?
N squared.
N squared. Why?
You have to multiply all the top digits for each bottom digit.
Okay. When you do long multiplication, exactly, right? So you multiply this with this, and you write that down here. Then you multiply this long number with the next one, and you write that down there. And you multiply, and you write it down there. Isn't that what you do? Okay, but you're not done yet. You have to add everything. What is the running time of that? Another? N. Is it n? Why is it n? Oh, you're adding everything up. Come on, you've been doing this for what? I don't know. 20 years, or maybe you're not 20 years. I've been doing it for more than 20 years. You're much younger than I am. At least 15 years, no? You've known this for at least 15 years. Surely you should be able to tell me how long it takes to multiply two integers. How many operations? Just count, normally, right? You're right. So first is n squared. Why? You just have to multiply. Actually, even that, let's be a little careful. How long does it take to multiply this long thing with that? So you'll do what? 5 times 3 is 15. You put a 1 down there. 9 times 3 is 27, 28, so on and so forth. Each multiplication here is one operation. You're writing down the carry. Then you multiply again and you add with the carry. So it's two operations. Then you write something down and you put another one. Essentially, it's O of n operations, right? And if it's binary, it's even easier. So suppose this is binary. What do? If there's a 1, you write down the whole thing. If there is a 0, nothing. So you just put, I'll just put an X over there, or I'll put a star, like nothing there. Then you find a 1, so you write down the whole thing again, starting from here, right? So you go 1, 0, 1, 1, 0, aligning this up correctly. Right, and then there's another no up there, so you put a star there, I'll put a star there, I'll put a star there, and the next one I'll write down over here, so on and so forth. So each of these takes O of n. Whether you're doing it in binary or in any base, it doesn't matter, because the number of operations is still a constant. Right, if you just think about how many operations you need. What about adding it all up? So now what do you finally have to add? There are n potentially integers, each of which has a length of O of n, because technically as you shift, it's moving, but it's only going to shift by at most n positions. So you're adding n integers with n bits, or n integers with n digits. How long does that take? How long does it take to add 2 integers? Just 2 integers, how long does it take? O of n. So how long will it take to add n integers of n bits? N squared. So it's not n, it's an extra n squared to add everything. Right, because you have to think about what you're doing when you're adding this column up. You have to look at everything in here. That's n things to look at. So each column over here is n operations. Right? So O of n for writing down each of these things, that's O of n. And then the final addition is O of n squared. Indeed, it's theta of n squared. It's basically n squared. So long multiplication runs in theta of n squared, right? Addition runs in theta of n. It's just linear, which is not surprising given what you know from grade school. Addition is easy and multiplication is harder. But this is just long multiplication. Can you actually beat long multiplication? So just to put this in another context, if you think about it a bit, this is a circuit of size theta n square to multiply 2 n bit. You can convert all of these operations into gates, because in this case you're just taking the AND of these 2 bits and writing it there, the AND of these 2 bits and writing it there. So each bit over here is the AND of 2 input bits, right? And then to add, you also know that you can basically do like an OR and a carry, and you can, there's a little circuit that adds 2 bits. So you can add all these bits using those circuits, called an adder circuit, right? So to add 2 bits, there's some O of 1 sized circuit. I can write it in terms of gates. So if you think about what long multiplication does, it actually gives you not just an algorithm, it also gives you a little circuit that you can write down. I hope you understand what I mean by a circuit, right? AND gates, OR gates, NOT gates. Yes? Just using AND, OR, and NOT, you can. People have to implement this inside your hardware, right? Because obviously your hardware is multiplying numbers. How is it multiplying? Huh? There's a little circuit inside your chip that multiplies. So whenever you do any operation, eventually if there's a multiplication, If you remember your architecture, you build an ALU, right? You build this arithmetic logic unit, which has a multiplier in it. Usually the multiplier will use the adder over and over again, which is this. So you need quadratic size, whereas for addition, you need linear size. The size affects how you build the chip. The more transistors and gates you need to put in, the more expensive it is. So it's natural to think about whether you can do it better. Because now, this is not obvious that an algorithm becomes a circuit, but in this case, hopefully you see it. In general, you can have some conversion procedure. So it was in this context that I don't know if the name sounds familiar. Kolmogorov was one of the preeminent Russian mathematicians in, I think, like 1963 or 63, asked, can we do better? And he thought the answer was no. He thought that this is the best you can do. That is, if you want to multiply two n-bit integers, you need a circuit which is quadratic size. Does the question make sense? And so the story is he basically held a conference and proposed this. He said, I want to study this question, and I don't think it can be done. And in the audience was a graduate student whose name was Karatsuba. And Karatsuba in 1963 gave a better algorithm. Like, he showed that you could do it less. I'll show you the algorithm. It's basically divide and conquer, which is remarkable that 2,000 years people have been multiplying. And a graduate student sitting in the audience looked at it, he used divide and conquer, and he did it. So apparently he actually did it, told Kolmogorov, and kind of just left. Kolmogorov got so excited that Kolmogorov wrote it up, gave talks everywhere without telling him, even wrote the paper with his name on it without telling him. So in the end, he only found out about the paper because someone gave it to him. And it had his name on it, but it was basically his algorithm. So let me tell you about how this is done, okay? Because it's a remarkable piece of math, or computer science or whatever you have. Does the question make sense? Just multiplying two n-bit integers. Okay, so let's think divide and conquer. So I'm going to write my integers as follows. So I want to say I want to multiply x and y. Okay? And x and y are n-bit integers. Okay? Now I'm going to write x as follows. I'm going to say, so think of x as a string, right? So let's say I divide the string. So I'm going to divide x into two parts, which I'll call xl and xr, yl and yr. That's the left and the right parts, right? Let's just assume for now that n is a power of 2. It's just going to make things easier. I don't have to take ceilings and floors, but everything is going to work otherwise. Okay, so x and l, these are of size n over 2. So another way to think of this is xl times 2 to the n over 2 plus xr.
Professor, the projection is blurry right now.
The projection is blurry. Okay, that is, hang on a second. Okay, so I think it was just the camera doing something fuzzy. Now it should be better. Yeah. Sometimes these clever cameras, like they try to be too smart, and they will actually make things blurry when it can be quite clear. So All right. And so what is y? That's yl times 2 to the n over 2 plus yr. Right? So no surprises here. So what is x times y? Just use the distributive law, right? And you'll get it's xl yl times 2 to the n plus the cross term xl yr plus xr yl times 2 to the n over 2 plus xr yr. Indeed, there's nothing about binary that's here, right? I mean, if you had treated these as digits, then instead of 2, you would write 10. It works in any base. Is formula clear? Right? So now each of these are smaller multiplications, right? Because now I'm multiplying two n over 2 bit integers. Okay? So here's my overall algorithm. I could say recursively compute xl yl, xl yr, xr yl, and xr yr, and then add xl yl 2 to the n plus xl yr plus xr yl 2 to the n over 2 plus xr yr. And the addition is quite easy. So here's one addition. That's one addition. This is just a shift. This is a shift by n over 2 bits. Right? And this is a shift by n. Right? And then I could just shift and add everything. So far, so clear? You see the divide and conquer algorithm? Questions? Okay, so let T of n be the worst case running time for inputs of length at most n. How long does that take in terms of T of n? What would you write for the first step?
4 times t n over 2.
4 multiplications of half the size. Clear? 4 multiplications of half the size. Right? 1 multiplication, 2, 3, 4. So this is 4 times t of n over 2. Okay. How long for step 2? Somebody else? How long does it take to do step 2? So you have found XLYL, you have found XLYR, XRYL, XRYR. How long does it take to do step 2? How many bits are there in XLYL, roughly? Like, how many bits do you expect? How long is that output? Yes? Anyone? We just discussed, right? Adding. How many bits does XL? XL has n over 2 bits. Right? If you multiply two strings, multiply two integers that have n over 2 bits, how many bits maximum could there be in the product? N. At most n bits, right? Because when you multiply two numbers, the number of digits that you get is at most the sum of the digits, sum of the number of digits, right? You multiply something with 3 digits times 3 digits, you'll get at most 6. You won't get anything more than that. So this has at most n bits. You're going to shift that by n bits. These things have at most n bits. You have to add them, then you have to shift and add. So how long is the whole thing going to take? Okay, 3n O of n. That's why we use the O notation, right? So that you don't have to worry about the constant. It's basically O of n. Does everyone see that? It's O of n to do this. So this runs in O of n. So 4 times t of n over 2 plus O of n. That's what it is. Okay? So we get t of n is at most 4 times t of n over 2 plus O of n. That's a recurrence. And of course, t of 1 is O of 1. Right? So let's solve this recurrence. Again, yes, you can use the master theorem, but I want to draw the recursion tree to see exactly what's going on. Does everybody understand what's going on? It's clear? Okay. So unfortunately I think somehow this thing, it thinks it's a white screen and then just decides to defocus. Okay, so if this happens again, then I might switch the camera. Just those who are remote, just let me know if it happens again. All right, so let's draw the recursion tree. You start with n. 4 children with n over 2. This is going to have 4 children, n over 4, so on and so forth. So how much work happens here? At most c times n. How much work happens in this node? At most what? How much? C times n over 2, right? Because it's O of n and n is the size, right? So you could write this is c times n and this is at most c, right? Cn over 2. How much over here? At most Cn over 4. Okay, let's do the total work per each level. At most c times n. How much over here? Add this up over all of the levels. How much? 2cn. How much over here? 4cn, right? Because it's cn over 4 times number of nodes, which is 16. 4cn. You see a pattern here? This is going to grow exponentially. If you do it for the next step, what you'll get is 2, 4, you get 8cn. Wait, well you get, yes, you'll get 8cn. Because in the next level, you'll have, let me make sure I'm doing this correctly, you'll get cn over 8, sorry. You get cn over 8, and how many nodes do you have? 4 times 4 times 4, 64, so you'll get 8cn. Indeed, if you look at the ith level, what you get is n divided by 2 to the I. Right? So the work over here is c of n divided by 2 to the I. But how many nodes do you have? You actually get 4 to the I nodes, because there are 4 children at each stage. So when you do all of this, what you get is you get 2 to the I cn. Does this make sense? So this is interesting, right? The number of recursive calls is growing faster than the decay in the size. So as you go down, the amount of work that you do in each node is decaying exponentially. Because it's going down. It's Cn divided by 2 to the I. It's like merge sort, right? As you go down, the inputs become smaller and smaller exponentially. But the number of calls is growing even faster than that. So that's why the amount of work in each recursive level is going up. Okay? So let's sum everything up. So the sum is at most summation I going from 0 log base 2 of n, ceilings, floors, whatever have you, 2 to the I Cn. I is equal to 0, log base 2n, 2 to the I. How much is this? Up to O's, just give me an O bound. How much is that? Sorry, this is fuzzy again. What I'm going to do is I'm just going to remove this altogether. Maybe use that, although it's less, maybe it's less quality. Hopefully this is going to be better. Sorry about that, those of you who are remote. Okay, yeah, so tell me, how much is that? It's an exponential sum, right? What did I tell you the principle was? Yeah, go ahead.
Sorry, again, for the log to the n, and for the height of the tree?
Yes, that is the height of the tree, right? Because that's the number of levels that you have. So how much is that? Up to O's. Just give me an O bound.
N squared?
Why n squared?
Because you said like the last term matters.
Okay, the last term. How much is the last term?
N
Okay.
and multiply by Cn.
Oh, the whole thing. Yeah, sure. The whole thing is n squared. Yes, I was asking you how much is the thing in the square. Yeah, in the, okay, the deformed rectangle that I've drawn. Right? The sum is dominated by the last term. Remember that? Exponential sum. The last term is what? Last term is 2 to the ceiling of log base 2n, whatever. This is just O of n. So it's n or 2 times n. At most 2 times n. So this sum over here, the sum is O of n. Actually, it's at most, you can even argue it's at most like 2 times n, or well, maybe a little more than 2 times n. So the whole thing just becomes O, keeping the constant in, n squared, because this gives you an n and that gives you an n. Great, so all I did was I went through all this work. I did long multiplication again. Does that make sense? You do divide and conquer this way, and you get back n squared. The reason I wanted to show you this is, look, if you do 4 calls of half the size and linear work, you get n squared. So if you do this algorithm over here, which seems like it's a lot more clever, it's just n squared all over again. Any questions? And that's not what Karatsuba did, right? Because that would have just been n squared. He's doing something more, which we need to see. Okay? Any questions about this? It's very subtle, so please ask me questions. Like, please make sure that you understand all these steps. Okay, let's go back. What I said was I will give you a divide and conquer algorithm to multiply 2 n-bit integers. It makes 4 multiplications of half the size, and then does some linear amount of work to combine everything together. Right? But when you solve that recurrence, you are back to n squared. It gives you a different algorithm. This actually is different from long multiplication. Because the way that you'll put things together will be different, but it's the same. It's the same asymptotic running time. Probably the constant is even worse here, because you'll be splitting things up and adding them. And actually, I'm not sure, but probably. Any questions about this?
So it's easy to give an example of how this works?
Sorry?
Is it easy to give an example of how this works?
How this algorithm works?
Yeah.
Sure. So this is puzzling you.
Yes.
Do you understand merge sort?
I do, yes.
So this is like merge sort, but I'll give you an example. But shall we stick with bits as opposed to digits? Just because then I don't have to, So I don't know. We did this, right? So 1 0 1 1 0 0 1 0 times 1 0 0 1 1 1. So this is XL, this is XR, this is YL, this is YR. So what we're going to do is we'll multiply 1 0 1 1 times 1 0 0 1. Right? That's XL YL. Then we have to multiply 0 0 1 0 times 1 0 0 1. It's this product. Then you multiply 1 0 1 1 times 1 1 0 1 and 0 0 1 0 times 1 1 0 1. Those are the four products that we need to get. Now, each of these is going to generate four products, because you're going to split this in half. And then what do you get over here? So you get 1 0 1 0 times 1 0, 1 1 times 1 0 times 0 1. Right? Those are the four products from here. I'm not going to write them all for everything, right? This, let's just go ahead and do it, right? As opposed to, technically you could divide this even more, but let's say we know how to do this, right? So how much is this going to be, right? Now to combine these, we multiply this by, so here n is equal to 4, right? And so you have 2 to the 2. 2 to the n over 2 is equal to 2 to the 2, which is what? Which is 1 0 0. So if you go back to our formula, remember, let me write down the formula here. Just write it down here. XY is equal to XL YL 2 to the n plus XL YR plus XR YL 2 to the n over 2 plus XR YR. Right, that was the formula. So let's just go back. So we multiplied this by 2 to the n over 2, which is 100. We're essentially multiplying this by 2 to the n over 2. Multiply this by 2 to the n, which is 1 0 0 0 0. Sorry. Right, multiply this by 2 to the n, so 4 zeros. We multiply this by 1 0 0, multiply this by 1 0 0, and multiply this with nothing, with just 1. And then we add all of these things together. So what we get over here is 1 0 0, and then we get 1 1 0 0 0 plus 1 0 0 0 plus that. Then we just go ahead and add all of this stuff up. And when we add all of these things together, then we get this product here. Then we apply the same rule with all of these. Right? It just seems like a more complicated way of doing something that you know how to do in an easier way. Is this clear? It's clear how you do this? Okay? But let's go back to this formula. So this was Karatsuba's sort of great insight. He said we can compute these three, so you want these four numbers. But you don't really need both of these, you just need their sum. So he said, can you do 3 multiplications to get these 3 numbers? As opposed to doing 4 multiplications to get them. So 4 is easy because you just compute each of these. This is what he observed. He said, take this. XL plus XR times YL plus YR. It's very strange. What you're doing is, in this case, you would actually you're adding XL plus XR and YL and YR, something you would never do in long multiplication. You never add things within the same number, right? You only cross multiply. You never take something and just add the things together. That seems meaningless. Except he said that if you compute this and you subtract out XL, YL, and XR, YR, then what you get is exactly XL, YR plus XR, YL. You can see this, right? So XL, YL cancels out, XR, YR cancels out. What you have left is exactly the middle term. So this is genius. I mean, like, why would you actually add up things within the same number, within the same input? Like within X, you're adding up XL and XR, and you add YL and YR. So you compute this product. You have to compute XL, YL, and you have to compute XR, YR. So you compute XL, YL, you compute XR, YR, then you add these and then you compute the product. So you do 3 products. You do more work in the addition. There's more work because you have to add XL and YL. But that only affects the constant term. So this is the cleverness. When you trade off the addition and multiplication, you do more work in the addition, but fewer recursive calls. It's in your benefit. Because the recursive calls explode exponentially. So anything you can do to reduce that will eventually save you. That's what happens in divide and conquer. Which is why it's very hard to wrap your head around. But is this clear? Okay, so now let's write the algorithm for Karatsuba multiplication is as follows. So first step is compute what I'll call Z1, which is XL plus XR, and Z2, which is YL plus YR. Recursively compute XL, YL, XR, YR, and Z1, Z2. Okay? The third step is add XL, YL 2 to the n plus the middle term you get by a subtraction. You say Z1, Z2 minus XL, YL minus XR, YR times 2 to the n over 2 plus XR, YR. Okay? Does this make sense? because this middle that I'm computing is exactly this formula here. Any questions? It's clear? This is the algorithm now. What is the runtime of the first step? First step? O of n, right? Just two additions. Second step. How many multiplications? 3. Each of size? What is the size of XL? N over 2. What is the size of XR? What is the size of Z1 and Z2? Of course, it's O of n, but now you have to be careful because you're treating the size of the input. How big a string do you get when you add two strings of size n over 2? 2 bit strings. If you add two 10-digit numbers, how many digits will you have in the sum? If you add two n-digit numbers, how many can you have in the sum? N plus 1, right? I mean, you just get a carry at the end. So the size of this is at most n over 2 plus 1. You'll have to believe me that I can just treat it to be n over 2. You can do it more carefully than n over 2 plus 1, but essentially it's n over 2, asymptotically. Sort of believe me on that. Like, you can make the recurrence work in general. Okay, but I don't want to put it because it'll just make the math complicated. You can then prove, anyway, you can do it by induction eventually. But what you get over here is that this is essentially Z1, Z2 have at most n over 2 bits. It's essentially size half. If it was n, then you're hosed, right? Because if you're converting one multiplication of n bits to another multiplication of n bits, you're not gaining anything. So smaller. So think of it as what you're doing in this example here is you're going to do 10 plus 11, whatever. 1, 0 plus 1, 1. And 1, 0 plus 0, 1. And then you multiply those things together. So maybe the way to think of it is, let's go back to this example here. The 3 multiplications you will do is you'll do 1, 0 times 1, 0 as before. You'll also do 1, 1 times 0, 1 as before. The middle one that you do is kind of funny. You're going to add 1, 0 plus 1, 1. How much is 1, 0 plus 1, 1? It's going to be, I think it's 1, 0, 1. Right? 1, 0, yeah. 1, 0, 1 plus, you're going to add times. This is the third multiplication that you do. 1, 0, 1 times 1, 1. Because you're adding these two things together. You add these two things, so you get 3 bits. But essentially it's n over 2 plus 1. Okay? I'm going to fudge and just say that it's n over 2. It works overall. And then once you multiply these, then you'll take this and subtract these two things out. And when you subtract those two things out, you get exactly the middle terms. This is 3 Tn over 2. And finally, the last step is again O of n. Right? Just n-bit additions. Does this make sense? Do you see that? You see the cleverness that 3 multiplications are enough to give you those terms. as opposed to 4. So if you look at this picture here, you only need to do 3 multiplications as opposed to here you need to do 4. Except you have to do extra work to get these things. But that's just O of n, which is sort of you have to do anyway. It's only a constant increase per call, but the total number of calls will reduce exponentially. That's the way to think about it. In the recursion tree, if you do more work in each node, but you can reduce the number of nodes, it might still be a benefit. As long as you can get the reduction in the number of nodes to be much more, that factor reduction is more than the amount of work you need to do. Right? There's some trade-off. But it turns out, with divide and conquer, the trade-off is usually in favor of reducing the number of recursive calls. You want the recursion tree to shrink, and you can do a little bit more work in each of the nodes. Does that make sense? So if we write down this recurrence, you get T of n is at most 3 T of n over 2 plus O of n. So before we had 4, now we have a 3. So this is actually a good time to pause, take a break for a few minutes, and then when we come back, we'll finish this. I'll take any questions you have in the meantime, but you can stretch and breathe and take everything in. All right, so let's continue. So any questions about where we are so far? Maybe I'll just do a quick recap. So remember, we are applying this formula here. xy is equal to xlyl times 2 to the n plus xlyr plus xryl times 2 to the n over 2 plus xryr. So if you step back, what you say is you need three quantities you have to compute three quantities: xlyl, xryr, and the cross terms. Now, the simple way of doing divide and conquer, we'll say, well, to compute the cross terms, it is the sum of two products. Compute those products, take the sum. Your problem is you now have four products to compute, and you end up with a recurrence that just gives you n squared. So Karatsuba's observation is that you can do it with three multiplications, except you now have to be clever about what multiplications you choose. So if you compute xl plus xr times yl plus yr, and you subtract out xl, yl, and xr, yr, then you get exactly xl, yr, and xr, yl, which is that middle term. How he saw this, I don't know. Right? That was a stroke of genius. But once he got this, then the divide and conquer formula just works. Then you just plug it in. You say, okay, so what you compute, or first you compute xl plus xr, yl plus yr. That's linear time. Observing that these have at most, I guess, n over 2 plus 1 bits. Suppose n over 2 plus 1. So technically this should be 3 times tn over 2 plus 1. Or it's like 2 times tn over 2 plus tn over 2 plus 1. But you'll see that, okay, I will show you. Basically what you do is you do some quick and dirty calculations to guess the answer. Then you write down the full thing and do induction. That's usually the way that you approach these things. So the two products are the same ones as before. The third one is a new product. But this takes n over 2 plus 1 bits. It's one extra bit. But we'll see that that actually doesn't, in the end, it's not going to matter. Then to compute the middle term, you take the product and then you subtract out these terms. That gives you that middle term using this formula up here. Right? This is Z1, this is Z2. Is that clear? So then you compute using the formula. This is an O of n computation. Okay. Which gives us our recurrence here. Again, it's still not obvious what this recurrence is going to give us. So let's go ahead and do our usual recursion tree. Where's the thing with n? This is at most c times n, right? Because we can say this is cn, and t of 1 is at most c. So this is the work. Now this makes 3 calls. N over 2. And this makes 3 calls with n over 4. So on and so forth. So each of these, this is now cn over 2. The amount of work that happens here is at most cn over 4. Let's take the sum. This is at most cn. How much is this? Three cn over 2, exactly. How much is this? Nine cn over 4, exactly. Do you see some relationship between 9 cn over 4 and 3 over 2? What is it? Square. what happens in the ith level is essentially you get 3 over 2 to the power I Cn. Okay, so this is important to observe. The denominator, the 2 to the I in the denominator, is the amount of work, which per node is decreasing just like before, decreasing exponentially, just as before. If you do merge sort, you get the same 2 over I in the denominator. The numerator was previously 4 to the power I, now it's 3 to the power I. The constant may have gone up, but see that the number of calls is decreasing exponentially. So let me write this down. So maybe instead of C, I'll call it C prime. Okay? C prime is the one that you get for Karatsuba, and C is the constant you get for the other divide and conquer. So the sum over here is the sum. What is the height of the tree? Sorry?
Log n.
What base?
2.
Is it 2 or 3?
Isn't it 2?
No, I'm messing with you. It's 2. Because it's the exponent is just going down by 2. So it is 2, exactly. It is 2. Log base 2n. 3 over 2 to the power I, I'll say C prime n. Right, so C prime is what? Before, what we got was sum, I going from 0 to log base 2 to the n, 2 to the power I Cn. So C prime is bigger than C, but this sum is decreasing much more sharply. So it pays off. Okay, so we have to compute this. Now, what did I say? When you have this sort of exponential, you just look at the last term. It's essentially O of the last term. So you get O. Okay, so C prime n, that's just this, times 3 over 2 to the power log base 2n. Before we were getting 2 to the power log base 2n, which is n. But now we get 3 over 2 to the power log base 2n. Okay? Okay, so I'm just going to do a little bit of manipulation to this. The n cancels out with the denominator. You get 3 to the log base 2n. Because the denominator is 2 to the log base 2n, which is just n. So what is 3 to the log base 2n? Let's write this in a form that is more convenient for us. Okay, so I'm just going to say that I can write this as what is 3? That's log base 2 to the 3, log base 2n, right? I'm just writing 3 as 2 to the log base 2, 3. Switching things around, I get n to the log base 2, 3. Now this is something like 1.58. Right? You could believe like root 2 is like 1.4, right? So 2 times 1.4. 2 times 1.5 is 3, so it's a little more than that. So what you get is basically you get O, I mean ignoring the C prime I'll absorb into the O, is n to the 1.58. Technically it's O of n log base 2 of 3, but this is essentially, I mean, n to the 1.58 is an upper bound. Okay? So you can actually multiply two n-bit integers with n to the 1.58 operations, meaning that, just to give you some context to what this is, just to think about it a little bit, suppose n was roughly, I don't know, 100,000, which people do when they do these, like when they try to find large primes, the great internet Mersenne prime search where they do these large computations, you might have some, they actually multiply, says n is not the number, but rather the number of bits, which is huge. So if you did long multiplication, you're looking at something like 10 to the 10 operations. If you're doing Karatsuba, you're looking at something like 10 to the 5 times 1.58, whatever. But this thing is going to be like, maybe this thing is going to be, I think it'll be less than 10 to the 8, right? So it's like 100 times faster at that level. But you need to go pretty big. The constant is worse. There are lots of things to consider. Even I think when you have 1,000, like you see the difference. Maybe if it's like 10 or 20, you won't see anything if you're doing things like the kinds of multiplications we do, 64-bit. It's probably not enough to start seeing anything significantly, but when you do larger things, you will. Okay, but this still raises now a very interesting question. Okay, this seems like very strange bound. N to the log base 2 of 3. Is this really the right answer? Anyway, but I first, before we go there, I want you to make sure that you understand this. What we did was we wrote the recurrence with a 3 as opposed to a 4, and we get n to the 1.58. Now remember, I said that I fudged the calculation. It should actually be the right recurrence. The correct form would be t of n is at most 2t over 2 plus t of n over 2 plus 1 plus c prime n. Right, because there was an extra bit there. But you'll see that if you actually prove this bound by induction, the n to the log base 2, 3, it'll work. So you could just prove it by induction directly. And that's usually how you would do it. You would do all this calculation to kind of guess the right form, and then you prove it by induction. Indeed, if you did something like n to the 1.6, it will just work. Okay? So this is Karatsuba multiplication. Basically getting n to the 1.58, which was a surprise when it happened, because nobody expected that you could beat long multiplication. The history of this is, it's a very fundamental problem, right? What's more fundamental than multiplying integers? Interestingly, the story of this is, it's only recently that there has been some resolution. So since then, Toom and Cook, and this is right after the Karatsuba. I think Karatsuba was like 62 and this was 63, so I may have messed up my dates. Said, instead of you do divide and conquer, breaking into 3 parts. Like you take x and you break it into 3 parts, and then you try to compute various kinds of additions amongst them. You can do it, and you get an improvement over Karatsuba. Like it's not a major, like you get some, instead of n to the 1.58, it becomes n to the 1.53 or something. But then the big improvement since then was Schoenhager and Strassen. And this is 71, where they actually they go n log n. Okay, this is a log n, but it's like n log n. This uses something called the fast Fourier transform. It also, at the heart of it, has divide and conquer. And the n log n comes from a merge sort like recurrence. But it uses a much more heavier technique called the fast Fourier transform. And so the question was actually, do you need the log n? Now at this point starts becoming really mathematical. Like this algorithm, I think this is probably reasonably practical for large sizes. Although I think the real implementations that really scale up to like tens of thousands of digits do combinations of doing this at large sizes, then at small sizes they do Toom Cook. Like they kind of engineer those things. Just like if you think about sorting in practice, often you'll do quicksort up to some stage and then you do insertion sort after that, because it's actually faster at smaller place instances because of caching and things like that. This was actually the state of the art until Führer which I was a grad student when this came out. This is a pretty big deal when it came out, where he got something n log n. He gets something called 2 to the log star n. I don't want to get into what this is, but it's like some improvement. For this, there's a lot of math involved. And then finally, Harvey and van der Hoeven in 2019 gave an O of n log n algorithm. And this is, it's a very complicated mathematical result, and this is actually finally published only in 2021. Like, I think the archive version, like the public version, came in 2019. It was published in, and then you can ask, can you beat n log n? It's believed that you cannot do better than n log n. That fundamentally multiplication is harder than addition, but no one knows how to prove that yet. So this is sort of the story of multiplication, where it all started with divide and conquer. And again, even Schoenhager-Strassen, which I was going to show you Schoenhager-Strassen, I could. In a lecture, I can show you the fast Fourier transform. But unfortunately, we don't have time this quarter. Okay, any questions? So it's a remarkable history coming up all the way to contemporary mathematics on just how to multiply two integers. In this vein, okay, so any questions about this? Or any questions? I don't know too much more about the history, but I can tell you whatever I know. Yeah?
By saying you're using the fast Fourier transformation, are you saying decrease the amount of multiplication by using convolution?
Essentially, yeah.
In frequency domain?
Well, I mean, instead of thinking of, you could basically, what you can do is, if you think about what multiplication is, if you write it out, it's like a convolution, because you can think of each bit has a shift, and then you're multiplying two bits with different shifts, and then you're adding things where the total sum of shifts is the same.
It's like a time series.
It's basically a convolution. It's like polynomial multiplication. So you can use a polynomial multiplication algorithm, and you use the FFT to do that. So you convert the integer multiplication to a polynomial multiplication. You use an FFT for that, and then you kind of convert it back. And that conversion leads to the extra log n work. Yeah. But yeah, you basically treat it as a convolution. Yeah. Okay, so the next story is with matrix multiplication, where we'll see a very similar phenomenon is going to happen. So you want to multiply, let's just say, multiply two n cross n matrices. Okay? So you compute C is A and B. And so here's A, here's B.
Is it dot multiplication?
Sorry?
Is it dot multiplication?
No, standard matrix multiplication. What do you mean by dot multiplication?
I thought like a fair row with
Standard. I mean, not entry-wise.
yeah.
Whatever you want to call it. Okay, so how long does this take? So if you look at C, and you look at the ijth entry in C. How do you get the ijth entry? You take the ith row, you take the jth column, and then you take the dot product of these as vectors. Right? So what you get is Cij is equal to the sum over all k going from 1 to n of A I k b k j. Right? That's how you do matrix multiplication. Now, from grade school, we're moving to high school. Let's look at a problem that you did in high school. How long does this algorithm take? So if you just follow this approach, how long will it take? N cube. Why? Why n cube? Quick reasoning.
You do like n multiplications and additions for each like spot in the final.
Exactly. For each entry, you do n multiplications and then n additions. Right? So each entry is computed in O of n time. There are n square entries. Hence, basically, I mean, you do theta n cube time. It's theta because it's exactly n cube, right? I mean, up to constant factors. So what you're doing is, if you think about it, you are computing n squared dot products of vectors. You think of this as a vector. These are, each column is a vector, each row is a vector. I'm sorry, the other, each row and each column. Treating them as, excuse me, treating them as vectors in the same dimensional space, treating them as vectors, and then you're taking dot products of vectors. Dot product of a vector is O of n, right? If you have two n-dimensional vectors, you just multiply and sum. And so, just as Kolmogorov asked, Strassen asked, is this really the best you can do? Matrix multiplication is one of the most fundamental operations that is there, let's say, in contemporary machine learning. Because everything under the hood in the end usually does a matrix multiplication. Whether it's inverting a matrix, whether it's solving a linear system, anything. Whenever things are being solved, anything numerical in practice involves some matrix somewhere. Faster matrix so usually if you speed up matrix multiplication, you speed everything up. By everything, I mean everything. Pretty much, you can think of, how many of you have heard of the problem of least squares? Fitting least squares. Have you fit least squares? Have you seen it being done? You've seen people do it, right? It's a matrix multiplication under the hood, because you're solving a linear system. When you solve a linear system, often you invert a matrix. Inverting a matrix is related to multiplying them. You can convert all of these things, eventually do some sort of multiplication of matrices. Now, if you think about it, there are only n squared entries you need. And you're paying n time for each of them. Can you somehow do anything better? Just like we did for multiplication. So again, we can essentially follow the same pattern as before. And what I can do is, I'm going to sort of divide this into these parts here. And this is a submatrix, which I call C11, C12, C21, C22. A11, A12, A21, A22, B11, B12, B21, B22. So these are submatrices, right, of dimensions n over 2. And what you get is you get C11. So one way to think of this is C11 is A11, B11 plus A12, B21. It's like you treat this as a row, you treat this as a column, you multiply and add, and you get C11. C12, for this term here, you multiply this row with this column, so you get A11, B12 plus A12, B22. C21 is you do A21, B11 plus A22, B21. C22 is A21, B12 plus, A22, B22. Observe that these are all different. A11, B11 never appears anywhere else again. Then A12, so A11 gets multiplied with B11, A11 gets multiplied with B12, but nobody else. How many products do you have? So how many subproducts do you have? How many? Sorry? Yeah, I was right. Whoever said 8. Right? So you have 8. So you can compute each of these. Compute with recursion. So, and then when you compute, you have to add these. The addition is O of n squared. Because you're adding two matrices, or n by n matrices. So actually, in some sense, n is not the size of the input. The size of the input is n squared. But it's convenient to parameterize by n. Right? The size of the matrix is n squared, not n. So O of n squared is linear time, basically. Okay? So if you write the recurrence, you get T of n is at most 8 times T of n over 2 plus O of n squared. Because you'll do 8 multiplications with, n over 2 size matrices, and then you do an n squared to add everything up. Like add everything up as you have to do these 4 additions. Maybe even just copying, the data to the right place. Not surprisingly, if you work out the math over here, you'll get the T of n is O of n cubed. You'll just get the same thing all over again. Just like we did for integer multiplication, when you do the naive divide and conquer, it's equivalent to long multiplication. Naive divide and conquer here is just vanilla matrix multiplication. And so Strassen I think it's like 72 or 73. Again, in something that really surprised everyone, said 7 products are enough. Instead of 8, he did it in 7. Which 7? I'm going to write these down. Unless you get much deeper into the mathematics, it's actually, it's just like someone actually asked him, and he said he just sort of tried to show that you couldn't do it in 7 and then bumped up into it. So what he did was he computed these. So think of it as you want to compute these 4 products. Another way of thinking of it is you're just trying to compute the product of 2 by 2 matrices. You're just doing 2 by 2 matrix multiplication. 2 matrices with 2 by 2s. The naive way of doing it is 8 multiplications. Suppose you want to do 7 multiplications, but you can spend as much time in addition as you want. Do whatever you want in addition, but reduce the number of multiplications. So he gave these products M1. Again, it's this strange thing where you add within. Actually, I need my notes for this because I don't remember what these are. A21. How he came up with this is I have no idea, right? And people have come up with various pictures to try to memorize this. Right, so this, like, these 7 strange products. But let me just show you that. We'll zoom out a bit. So he showed that C11 is M1 plus M4 minus M5 plus M7. C12 is equal to M3 plus M5. Okay. C21 is M2 plus M4, and C22 is M1 minus M2. We don't have to do all of them, but let's at least do a few of them. So M3 plus M5. So if you see, it's A11 minus A11 B22 cancels out with A11 B22, and you get A11 B12 and A11 B12 A12 B22. So you exactly get that term there. A11 B12 and A12 B22. A1 and B22, A1 and B22 cancel out. Similarly, if you do M2 plus M4, you'll see A22 B11 cancels out with A22 B11. So you get A21 B11, that's the first one, A22 B21 is the second term. Now you do M1 plus M4 minus M5 plus M7. I won't do it, but you'll get C11. Now you can legitimately ask, how on earth did he come up with this? Even with Karatsuba, maybe you can like say, okay, maybe this he must have spent a lot of time. There is then a theory beyond this was developed. People have proven that you can't do it in 6. That still doesn't mean that you can't do anything. But I will continue. It's still, you can beat Strassen's algorithm, but let's. You cannot do it in 6 multiplications. But you never know. There could be a way of taking 3 by 3 matrices and then doing something way better. Or 4 by 4, right? So that nobody knows. I mean, okay, so what you get is 7 products are enough. Right? So these are all these strange products where you add things within the matrix and you multiply. You see that you're adding something within the matrix, also subtracting. Luckily, all the coefficients here are only 1s and minus 1s. But who knows? Maybe you could, multiply something by 2 and 3 and subtract things out. The recurrence that you get from Strassen, the Strassen recurrence is T of n is at most 7 times T of n over 2 plus O of n squared. You draw out the recursion tree that O log base 2 of 7. What is log base 2 of 8? 3, right? So if it's actually what you get over here is log base 2 of the number of calls. So if it's 8 calls, you just get n cubed. But with 7 calls, you get n log base 2 of 7, which you can see is less than 3. Right? And I think this is like it's like 2.71 or something. So you can do it essentially in O 7.1 or 7.3, I forget, one of those, right? So essentially it's like I think it's 2.71. Okay, so again, this shook the world because people never thought that you could multiply matrices better than this. Strassen's algorithm is implemented in practice in some places. It does give an improvement. Indeed, this was I mean, Strassen's algorithm has been known since the 70s. But doing an efficient implementation of Strassen is not that easy because it has certain cache issues. This was done in 2014 or so, and this was it's won a major prize in the numerical analysis group in Siam. It was a very celebrated PhD thesis. This was where essentially an implementation of Strassen was done in practice and shown that you could engineer it. There are tons of people who work on engineering matrix multiplication. It's that important. Of course, you can ask what is the best known. There's a long series of results. For a long time, there was one by Coppersmith, Winograd. This is, I forget, I think it's 80s or 90s, I forget. Maybe it's the 90s, where they got something like n to the 2.36 using a very complex algorithm that, at this point, beyond Strassen, the others are not practical. And then Vasilevska Williams. That's one person, Vasilevska Williams. She, and I think this is maybe 2000, maybe it's 10 or 12. It's fairly recent. Maybe, I'm just going to say it's 2012, although I could be mixing it up. And I think she improved that 2.35 something. This is because one needed a lot of fairly involved mathematics to do that improvement. The big question is O of n square. Is it possible? There are some people who believe that it's actually not possible, that you cannot do it in n squared. But, and of course, the other question, sort of the implementation question, is how to get practical variance of the theoretical improvements. So this is, I'd say, the big theoretical question and the big applied question. And I don't mean this implementation, you just have to implement. You really have to understand how the algorithm interacts with the architecture and try to come up with these things. And it's a very important research question on how a lot of these, how can these improvements be done. But anyway, so this is a good time to end. The main thing I hope you learned is Karatsuba multiplication I did sort of in great detail. I would like you to understand all the details of that. You can basically redo all of those details here. What you should do is work out that recurrence and see that it's n cubed. Work out this